Hey guys, welcome back. Got a fun day for you. Today's a very important day because it's actually the last new topic, and it's a very short and small topic. But anyway, the last new topic that we have for the entire unit. So what that means is next Wednesday we're scheduled, that's the 30th of September, we're scheduled to take the test for Unit 1. Much of it will be very similar to what we did on the quiz, so if you've already taken the quiz, of course most of you guys have, you already know how well you're prepared for that, and I've given you good feedback on that quiz too, so you can go back and make sure that you understand how to do all that stuff from the first 4 chapters. We're going to finish up Chapter 5 today with probability plots, normal p-plots in other words. Really easy, fun, kind of cool stuff, honestly. And the assignment's going to be a little bit longer, kind of like a review assignment, so you'll have, and most of them are all odd problems. I'll do the only even problem with you, so we'll get right through all that good stuff, and we'll spend the next 3 days reviewing and then giving a practice test, and then we'll take the test on Wednesday. Important thing that you need to know is that all of the homework is due next Wednesday. So this weekend, make sure you get caught up. There won't be a whole lot of videos. I'm not even sure how much of videos I'll be posting because we're just reviewing stuff. I'll probably just post solutions of me going through the odd problem or the even problems with you or something like that. Or I'll make a video. I'm not sure. But anyway, we'll try to get through this stuff pretty quick, and I won't try not to waste your time so that you will have plenty of time to get caught up on the homework. Once those grades go in after Wednesday, they're finalized. I won't take any more late work after that point. And your test scores also, if you do better on the test than you did on the quiz, your test score will replace your quiz score, so that's good news. It's kind of like doing a retake. Just focus on doing well on the test and it'll bring your grade up. Also, the curve is pretty generous, so if you guys saw that, you don't have to worry too much. But anyway, let's get right into it. So looking at great white shark links again, not getting into all that stuff, but we do want to look at, just point out a few things. When we put this data into our calculator, and I think I still left mine in list, or I'll look real quick. So shark links, I put mine in list 2. So whenever we put it into our list, we graphed out the histogram. So second stat plot, I'm going to do list 2. So second 2, okay, and then whenever I hit zoom 9, it uses the default window. This is the distribution we get. No, it's close. Okay, so it's close to that, but whenever we change the window so that it matches up here, so we're going by 2s from 8 all the way up to 24. It's interesting, going by 2s. Now it should match that one, and just hit graph. Okay, so yes, now it matches that one. But if we went by just shifting it from 9 to 25, so go to window, and instead I just shift it by 1, which is so weird. Then all of a sudden it looks, it looks almost exactly unimodal and symmetric. Looks exactly like a bell curve, like perfect. So what's crazy is whenever we graph the data, we want to make it into a bell curve, right? So let me go over here. So we graph the data, that's the actual distribution, which is our histogram, right? That shows us the actual shape of the actual sample or our distribution or whatever. And then we want to ask ourselves, is it close enough to a normal model that it's appropriate to use normal? So we ask ourselves, is it unimodal, is it symmetric, do we have any crazy outliers that we think is going to drastically increase our mean or standard deviation or something like that, okay? But it's kind of subjective, right? And if we look back here, there were 3 different graphs that we saw, right? So we saw the original graph when we did zoom stat, which looked like that. And then we see this one when we shift it from 8 to 24, because then it's easy to graph. And then whenever we shifted it by 1 here, it looked like totally different. I mean, they're all more or less unimodal and symmetric, but this almost kind of looks bimodal, right? So it's kind of subjective. And if you rejected this because it was bimodal, I could understand why you would, just as long as you gave me justification, right? So there is some kind of leeway when it comes to the test and stuff like that, just as long as you justify why you did what you did, okay? But we need a better way to be able to test to see if a normal model is appropriate without just looking at the histogram. Now the histogram will show us where the troubled spots are. So it looks like there's a little bit on the left that's kind of grouped together. It looks like we have a tail on the right, so it might be slightly skewed to the right. This also might be a potential outlier, et cetera, right? But then when we look at this one, there doesn't really seem to be any issues at all. Maybe slight tail on the right side, but very much unimodal instead of the other 2 that were bimodal. So it's really crazy that just shifting the categories or shifting the window size, the bin size, or shifting your range from your X values can change the shape of the histogram so much, and that's all the exact same data. The data didn't change. So we need a better way to be able to test to see, without just doing the histogram, to be able to test to see how appropriate it is to use a normal model that won't change regardless. So again, we need it to be unimodal and symmetric, where it looks like a bell curve. If it's skewed to the left or the right, we can't use it. Because we can't use mean and standard deviation, we have to use a median and IQR. Same thing if we have crazy outliers, far outliers, or gaps between the data, it's no longer appropriate. So what we end up with is something called a normal p-plot. So if we go to our graph here, and if you have the data in there, you could do it. If not, just follow along with what I'm doing. Whatever data you have, you could try it out. So what we're going to do for the normal p-plot is this last graph here. So now we know how to do all of them. This is our scatter plot. This is a trend line. This is a histogram, modified box plot, a box plot which does not show outliers. We never use just a regular box plot. And then now the last one is the normal p-plot, or a normal probability plot. The data list, I'm drawing from list 2, I believe. Yes, it is list 2. And then the data axis, we're going to graph this along the y-axis. You could do the x-axis, and I'll show you what the difference is. And then the markers, I like to use a plus sign because they're more precise. And you can choose whatever color you want. I'm going to go with red so it matches with what I have on display here. And then, oh yeah, we got to make sure we turn it on. So for plot 1, we turn that one on. Plot 2, I'm going to turn that one off. Yeah. And then plot 3 is off as well. Okay, so then we just hit zoom 9. Boom, there it is. Now, if I hit trace, it's kind of interesting. You might be able to see what's going on here. But our Y value is going to be 9,4. Does that look familiar? The 9,4 is going to be the length of the shark, right? The X value is a negative 2.27. So if you go down here, if we look at these, if you remember what those stand for, 0, negative 1, 2. So negative 2.27 is going to be the z-score. So it's negative 2.27 standard deviation below the mean was the shortest shark length, okay? So what we're doing is we're plotting the z-scores, right, which is what we have graphed out on the bottom here, standardized z-scores with the y plots of the actual data, okay? Which is kind of cool because what we should get is a more or less a straight horizontal line if it's appropriate to use a normal model. So let me see if I can, I don't know why it didn't quite work. Okay, so if I connect these dots here, does that look like it's roughly a diagonal line? To me, that looks pretty good. Now you're going to have some points that deviate from it. That's totally fine. It does have a little bit of curvature in it, but it's not like one giant curve going down or one giant curve going up. So this is actually just fine. And even though we had 3 different histograms, right, showing the different data, and some of them look bimodal, still looked like it was skewed to the right. Whenever we graph out the normal probability plot, it's more or less straight. I look at the general trend there, we're good to go. So that tells us that it's appropriate to use a bell curve. So here's another one that we have. These are the long jump links. I put this in list 3 for mine. And again, when we did zoom stat, we had this data. And whenever I redid the bin size to 0.15 meters, because it was easier to graph for you guys, then it looked all of a sudden unimodal and symmetric with a potential outlier on the right side. But not necessarily skewed anymore because it's the same bin size from here to here as it is to there. So crazy stuff going on here just from resizing the bin size. You know, stuff is shifting all over the place. So what we want to do is we want to actually graph out the the probability plot for that. So this is going to be my list 3 for me. It's going to be the long jump data, and then just hit zoom 9 again. And there it is, and you'll notice that's exactly the same thing that we have here. So looking at this, if we drew a trend line here, okay, so this one, it looks, and again, this could be moved down there. So it looks like it's more or less fine. You notice these values are less than we would expect. That's because of the kind of the lower gap here, but that's totally fine. So you can see where the issues are in the actual data itself. And no matter how we resize this graph or distribution on the bottom, we're still going to see precisely what's going on with the normal p-plot, and that's why we prefer it. So that looks straight. We're good. It's straight enough, so we're good. We can use a normal distribution for it. Number of states visited for this last year's data because I didn't have time to redo it, but you get the idea. If we look at the histogram itself, clearly skewed to the right. This is not going to work. And when we graph the data along the x-axis, you can see the data is much higher than what we would expect here. So if I kind of connect those two dots, you can see how far off everything is. It's not a diagonal line. And so you've got this curvature in the data that's not actually, I guess I could draw the curvature. So you got this curve in the data that's not following along the line that we would expect. All right, so what happens if we graph our data instead of along the x-axis, if we do it along the y-axis? So what's happening when we do the y-axis, here we can actually see the points. You can see that point matches up with that one, this one matches up with that one down there. And now instead of a curvature that's going up, now we have curvature that's going down. So you can clearly see if we connect those two dots, which I suppose that is the correct procedure to connect those two dots, you can see how both of them are deviating from the trend line. So it doesn't matter if you do the x or the y-axis, you get the same information. It just kind of does a reciprocal. All right, so that was it. That's the normal p-plot. It's kind of fun. I don't think you have to make any. I think I just graphed them all out for you, so you're welcome. Number 46, tires. The tire manufacturer believes that the tread life of a snow tire can be described by a normal model with a mean of 32,000 and standard deviation 2,500. Label the normal model 3,200 and 35,000 and 2,500 below. If you buy a set of these tires, what's the probability based on normal model your tires would not last 40,000? All right, so what I'm going to do is I'm going to write the tread life in thousands of miles. That'll keep me from having a really long numbers here. So 32 would be 32,000. And then each standard deviation, I'm going to go up. I guess I need to fix that. That should be 2.5. So anyway, and if we are changing the label here, it's totally fine. Everything here would be now thousands of miles. So that's going to go up to 34.5, 37, 39.5, and then going down by 2.5 for each standard deviation and go out as well. So the first question is, what's the probability that your tires would not last 40,000 miles? So all the way up to 40,000 or less than 40,000 is going to be pretty much everything we can see under here. So this is going to be around 100%. It's almost all the area that we could see there. To find the exact area under the curve, remember we're finding the cumulative density of the area under the curve, kind of like an interval. So we're going to do second distribution variables to the distribution menu. We're going to go to normal CDF, which is the second option. I don't like that. That was weird. Because it should give me the menu. Yeah, it should give you the menu. I don't know why it didn't do it. All right, so my lower bound's negative infinity, which is good. The upper bound, because I'm not using z-scores, I have to use the actual data. So I'm just going to do 40. You could do everything 40,000, but again, if we keep it consistent, we're fine. So I'm working in thousands of miles because it's easier. Centered at 32 with standard deviation of 2.5. And that's going to give me a probability of 99.93%. So 99.93%. Approximately what fraction of these tires can be expected to last less than 30,000 miles? So 30,000, somewhere about here. We want to find the area under the curve there. So I'm going to do the same thing. We're finding the area under the curve, so it's still the CDF. So the second option, going from negative infinity to 30 this time. And the mean standard deviation is still the same. So 21.19%. Okay. Approximately what fraction of these tires can be expected to last between 30 and 35,000? So now we're kind of measuring from the center, but it's not really a big deal. So from 30 to 35,000, that is so slick. All right, so same thing. Second distribution, CDF. Our lower bound this time is going to be 30. Our upper bound we said was 35. Still same mean and standard deviation, which will give us 67.31. Okay, 67.31%. All right, so we're good with those. Now we're kind of shifting a little bit. Now we want to estimate the interquartile range. Well, the IQR is going to be the 75 percentile minus the 25 percentile. So we need to find out what those percentiles are. So we know the area under the curve, we just want to work backwards. So instead of doing normal CDF, we're going to do the inverse normal, which is our third option. Now the area that we're going to do, if we're doing the IQR, that's the middle 50%. So I'm going to do 0.5. Don't do 50, do 0.5 because it's a percentage is with the decimal. And we don't want to do, we don't want z-scores. So instead we're going to put the actual data from our distribution in here. we're going to measure 50% from the center. If we do it from the left, it's just going to give us the mean, or the medium, or the mean, which is 32. So anyway, from the center, then hit paste. It's going to give us an interval notation. So our first quartile, excuse me, is going to be 30.3. Our third quartile is going to be 33.69. All right. So anyway, we subtract those two when we do that. So 33.69 minus 30.31, it's going to give us 3.38, or 3,380 miles. Now I know we did all of our work here in thousands of miles, but whenever we're interpreting our final solution, it's probably nice to go back to the original miles. But anyway, just kind of showing you how I would do it. Now we have, in planning a marketing strategy, which they do this stuff all the time, a local tire dealer wants to offer a refund to any customer whose tires fail within a certain number of miles. However, the dealer does not want to make too big of a risk, so they don't want to pay out more than 4% of those refunds. So that has to do with how much they're charging for the refund, or how much they're charging for the service, or whatever, how much they expect to actually have to pay out. So for what mileage can he guarantee tires to last at least 4%? So we want to know what is the lowest 4%. So it's going to be somewhere around here, right? Actually, it'll be beyond that line because it's 2.5 beyond 2 standard deviations. So somewhere around, let's just put it about right there. So how many thousands of miles can he guarantee with having 4%? So this area under the curve here, the probability of having to pay out there is going to be equal to 0.04. We want to know what is the value x for when that probability would be 4%. Okay, so we have the area under the curve, so we're working backwards again. So normal CDF, our area is going to be 0.04, and then this time we're measuring not 4% from the center but from the left, and then hit paste, and there you go. So 27.62, which is kind of where I was at anyway. So 27.62, or 27,620 miles he could guarantee for it. All right, so I think that's pretty much it. Yeah, that's it. I think the rest of all the problems are going to be odd problems, where the answers are in the back of the book, so you can try them out yourself. It's a mixture of all kinds of problems from Chapter 5 with z-scores and all kinds of good stuff. The only other one is 32, but that's very, very similar to what we were just talking about, so I think you'll be okay. All right, so I'm going to end the video. Yes, under 18 minutes. That's awesome. Hope you guys have a good day, and remember, you guys got about a week, yeah, exactly a week from today to have all of your work turned in. So join me on the live office hours during tutoring from 1 o'clock to 2 o'clock if you have any questions. I'm here. I want to help. And yeah, I'll see you guys later. Have a good